So I want to do another example. This one is where we have an oblique asymptote. Now again, what we're going to do, let's look for the y-intercept. Now the y-intercept, we let x equal 0, and we find y. So what we get, y is x squared minus x plus 1 over x minus 1. Or y is 0 squared minus 0 plus 1 over 0 minus 1, which will be 1 over negative 1 or negative 1. So what this says is that when x is 0, y is going to be negative 1. I'll just keep that up here. It's one of our points. Now for the x-intercept, I'm going to switch things up. We're going to let y equal 0. We're going to find x. So in that case, we'll get 0, x squared minus x plus 1 over x minus 1. So we'll multiply both sides by x minus 1. So these will cancel. We'll get 0, x squared minus x plus 1. And this is sort of what happens generally, is we'll get this cancellation. So to find the x-intercept, we really just got to take the numerator, set it equals 0. Now if we try to factor this, it doesn't really work out. So let's sort of bring out the tool that usually can get us through the quadratic formula. So we've got a is 1, b is negative 1, and c is 1. So the quadratic, negative b plus or minus the square root b squared minus 4ac divided by 2a, or negative 1 plus or minus the square root negative 1 squared minus 4 times 1 times 1 divided by 2 times 1. And you're going to see that we get ourselves into a little bit of trouble here. We're going to get 1 minus 4, which will be 1 plus or minus the square root of negative 3 over 2. Now, these functions, we're graphing them on the xy plane. Now, on the xy plane, we're only dealing with real numbers. And we've got the square root of negative 3. So this means we're going to be getting an imaginary or complex number. And that just isn't going to work. So when we get something like this, this tells us we got to stop. So we don't get any x-intercepts here. So we have a y-intercept, we have no x-intercepts. Now let's take a look at some things that are very particular to rational functions. First off, vertical asymptote. Well, here's q of x. Let's set it equal to 0. Add 1 to both sides, we get 1 is equal to x. So we either have a vertical asymptote at x equals 1, or we have a hole at x equals 1. Well, we couldn't factor this even with the help of the quadratic formula. So this factor is not going to cancel into this. So this isn't going to be a hole. This is going to be a vertical asymptote. So now let's look at the horizontal asymptote or the oblique asymptote. Well, if we look at the degrees, the degree of p of x, the numerator polynomial, that's equal to the degree of q of x plus 1. You have to add 1 to the degree of q of x to get to the degree of p of x. Because this has a degree of 1 and this is a degree of 2, or what we end up getting is 2 equals 1 plus 1. So that means oblique asymptote. So what we're going to do, we're going to divide p of x by q of x. We'll get a line plus a remainder, and we'll just discard the remainder. Now to do this, let's use synthetic division. So 1 times 1 is 1. Add it, we get 0. 1 times 0 is 0. Add these, we get 1. And this is the remainder term, constant term, coefficient for x. So what we get is x remainder 1, or an oblique asymptote of x plus that positive 1 divided by the divisor, x minus 1. And as I noted before, the remainder term's not going to be important. It's going to go away. And the reason is, as we get farther away from 0, this is going to become so small it's irrelevant. So we're going to focus on this. Again, the horizontal asymptote or the oblique asymptotes, they're about end behavior. What happens when you're far away from x? For this remainder, as this x just sort of gets monstrously big in a positive sense or in a negative sense, this is all going to get very small. So we have an oblique asymptote of y equals x. Now there's a question we want to ask with this oblique asymptote though. Vertical asymptotes, off limits. You can't cross those if you're a function. No way. But you could cross horizontal asymptotes and oblique asymptotes. They're more like guidelines about how this function behaves as we get farther away from 0 in the positive or negative direction. So you could cross those. So let's see if we do. So to figure that out, we take our asymptote, whether it's horizontal or oblique, we set it equal to f of x. For x is going to be this. And really we're asking, does this hold true? Well, I can tell you it doesn't, because we've already performed like this division here, and we got x plus a remainder term, so it's not going to hold true. But if you wanted to go through with it anyway, multiply both sides by x minus 1. Or here, let me go through the steps. And again, this is really redundant. We've already performed this division using synthetic division. We got x with a remainder of 1, and clearly this doesn't have a remainder of 1, so it's It's not going to work, but let's just see that it doesn't. We'll just go through the steps. So we get cancellation here. We'll get x minus 1 times x is x squared minus x plus 1. Distribute the x. Right away, we're going to see these two are not the same. X squared minus x, but this one's got a plus 1. And again, if you want to go through the steps on it, subtract x squared. You'll get minus x equals minus x plus 1. And then finally, add it to both sides, and we get 0. It's supposedly equal to 1. No, it isn't. So this isn't true. So again, we can verify that our function will not intersect or cross over the oblique asymptote. So we've got that settled. The last thing to do is look for test points. So we don't have any x-intercepts. We just have a vertical intercept and x equals 1. And we need to pick some points to test. And there's nothing to pick. There's nothing where we could pick something between something. So we'll just do the far sides. Like, let's just say 0. And let's just say 2. Let's see what we get. Well, f of 0, we actually already know that one. F of 0, that was our y-intercept, and that came out to be, well, I'll go through the steps again. Well, that came out to minus 1, as we saw before. So that says we have a point 0, minus 1. Here, I'll make this little hash mark instead. So we have 0, minus 1. Now, f of 2, this will be a new one. F of 2 will get 3, comma 2. All right. So we've got some test points to work with. Let's graph this. All right. Now, we do have a vertical asymptote at x equals 1. And then we have an oblique asymptote, y equals x. And we also have a point, 0, negative 1. That's going to be right here. And I should put in my y-axis here just so there's no confusion. The y-axis was going through here on our test points. And then we have 2 and 3 right there. So let's try to graph this thing. Well, we know we can't cross the vertical asymptote no matter what. And the oblique asymptote, well, we discovered that we can't cross it this time. Other functions we might be able to, but not this one. So that means where can our function go? Well, it could kind of do something like this. It could do something like that. And okay, that's the best we can do here. We know there's a point here. And, maybe this could be a little farther down. Maybe it does something kind of like this. But this is just kind of a guess, just a rough estimate. And the same with this. Probably does something like this. And something like this. We just have to be careful, though. This one only has one y-intercept, so we should only be crossing the y-axis here. But I mean, this could be coming up a little bit farther up in here and then dropping down. Again, it's kind of a rough estimate. But there's a rough sketch of our graph. So if you have any questions, let me know.